Click the bell icon to get latest videos from Ekeeda.
Hello friends, welcome to this video where we are going to solve a problem based on to the concepts, the formulations of motion of electron in the presence of electric field, magnetic field and electromagnetic field that we have covered in the last 3 videos. Up till now in this chapter, microwave frequencies, the term microwave we are introduced various band designations you know very well. Microwave is the electromagnetic wave having the frequency range from 1 GHz to 300 GHz. With the knowledge of microwave devices based on to the vacuum tube platform or the semiconductor platform, now you are well aware with the various applications we have gone through. The units of measure also we have covered. Let us solve this particular problem. So it will be having a solid benchmark to start with the understanding of principles of operation to have the microwave tubes, the second chapter we are about to start. So for this particular problem, the problem statement is given to us. The problem statement is the inner cylinder of a radius, the radius is denoted by small a here, is the cathode, and the outer shell with the radius, it is denoted by small b, is the anode. So there are two cylinders, one inside another. The inner cylinder having the radius a is denoting the cathode terminal of the vacuum tube you can take, and the outer cylinder is having the radius small b is the anode terminal. A DC voltage V0 is applied between the anode and the cathode, and a magnetic flux density capital B is into the page. So you see here V0 is applied between the anode and cathode, so it will produce the electric field directed from the positive terminal to that of the negative terminal, and the magnetic flux density is also present inside the page. So for that purpose the diagram is of course the given. So what is asked into this particular problem, we have to adjust the applied voltage V0 and the magnetic flux density B to such levels that the electrons emitted from the cathode will just graze the anode and travel in the space between cathode and the anode only. Now for this particular case the diagram is given to us. The diagram is, so here we have the diagram, the two cylinders one inside another. So the inner circle is showing us the cross section of the inner cylinder here. So this is nothing but the cathode terminal. You know that cathode terminal is always negatively charged, and at the cathode terminal exactly, so the potential applied V will be equal to V0, and the outer cylinder that is shown with the outer circle, that is the anode terminal, which is always positively charged, and if you switch the positions from cathode to that of the anode, at anode the full voltage applied V0 as per the given problem statement is available here. Now in this particular structure, here we have the cross sign denoting the B bar inside the page. So it is actually the magnetic flux density, magnetic field is present here right from top to that of the bottom here. So in this particular structure, the radius of cathode and that of the anode cylinder are shown by small a and small b here. Because of the applied potential between cathode and anode, that is V0 here, you can see that the electric field will be directed from the anode terminal, which is positive, to that of the cathode terminal, which is negative. So this is the direction. So this is only the radially inward direction. So if the anode and cathode are of cylindrical shape, it will be quite convenient to work with the cylindrical coordinate system. Hence the electric field intensity representing this electric field is denoted by capital E suffix rho. So E phi component and Ez component are absent. The magnetic field is shown already here, and as for any of the vacuum tubes or the electronic device where the electron is the basic entity, so it is of course the path of the electron from the cathode terminal to that of the anode terminal. So here in this diagram we have the path of the electron that is diverted outwards from to the cathode towards the anode. So what is asked to us? The electron should only graze the anode terminal. It should not directly hit that anode terminal. So for that purpose, the electron motion has to be adjusted with the adjustment into the applied potential V0 and the magnetic flux. So let us solve this problem. So to look at the situation given into the current problem, we have also expressed with the help of diagram here. We write the two equations of the motion of electron in the presence of electromagnetic field here. So the first equation we shall be having, so the equation will be having d2 rho divided by dt square. It is the acceleration component into the radial direction rho here, minus it will be rho along with a bracket that is squared having the velocity component into the phi direction. So this is the left hand side, and the right hand side will be given by E divided by m in the multiplication to E rho minus E divided by m in multiplication to rho d phi upon a dt into bz component here. Now the second equation can be, so let us say this is equation number 1. Second equation is given as 1 upon rho. It will be having a ddt of rho square in the bracket. We have d phi upon dt here. So it is obtained as the ratio of E to m in multiplication to bz component into d rho upon dt. So as per the given situation into the diagram, the rho component and phi component are the only two possibilities for the electron, as it will be emitted by the cathode terminal and will try to reach the anode here. Hence only these two equations we have taken, where the acceleration component in the terms of rho component we have taken, and the ddt along with the ddt of phi here will be for the phi component here. Now from this second equation we shall be having the another relation. So the relation can be written as in the modified form. It will be having a ddt inside the bracket rho square. It will be d phi upon a dt. It will be equal to 1 upon 2 omega c, we can substitute, into ddt of rho square. Now the substitution here is, we can write where omega c is equal to E by m into B0, the initial magnetic flux density. Now in this equation we have 2 times time derivative. So if ddt, if you need to cancel out, you need to integrate both sides of this particular equation. So in that case we obtain rho square d phi upon a dt. So this will be obtained equal to 1 upon 2 omega c, the substitution that we have made, into rho square here. So this ddt and this ddt will be gone here, but the RHS will be added with a constant term. Now for us it is very important to know what is the value of this particular constant term. So for that purpose we shall be applying a boundary condition here. So as in the diagram we have the inner cylinder that is having the radius, let us say small a is given to us, and outer cylinder is there, the radius is small b here. So we shall be putting a condition that rho is equal to a, so that we shall be checking the relation at the boundary of the cathode terminal. Now applying the boundary, we write rho is equal to a. We get the above equation modified. We substitute rho is equal to a. So it will be a square in multiplication to d phi by dt, given as 1 by 2 omega c, already the substitution, into a square plus constant. Now at the cathode body, that is rho is equal to A, we are present. So at that particular point, d phi upon a dt, which is actually a velocity component in the phi direction. So it is the distance covered per unit time. So we can also denote it as v phi component. So this v phi component is equal to 0. So if the d phi component is equal to 0, the left hand side will be equal to 0. So in that case, to have this particular equation existed, the constant value should be equal to minus 1 by 2. This is minus 1 by 2 omega c into a square here. Therefore, we write the above equation, that is rho square into d phi upon a dt will be equal to 1 by 2 omega c in the bracket. Here we have rho square minus a square. So this is the equation that will be helpful to us. Now we shall be having the magnetic field existed here. So as we have already seen into the previous videos, if the two fields, electric field and magnetic field, are present, the magnetic field will not be changing the direction of electron if the directions of the electric field and that of the magnetic field are same. So for that particular case, the equilibrium equation that it was 1 upon 2 m v square is equal to E into V, the electron volt you can say. At this particular condition, the magnetic field will not be changing the direction of electron. So to look at this particular equation, we can write V square is equal to twice electron volt divided by m here, or simply E into V here. So this will be having the two components here. So the first component will be the rhoth component. So V rho square plus V phi square it will be here, and which can be expressed in the terms of, it will be having d rho by dt bracket square added with, here we have rho into d phi by dt bracket square. Now for the condition to only graze the anode, we can have the substitutions. So it will be rho is equal to b, that is the radius of the outer shell, that is the anode. We can have the potential V substituted by the applied potential V0. Then d rho by dt, the velocity component. At that particular case, it will be 0 after it reaches the anode terminal here. Then we can have the equation in the form b square in bracket d phi by dt bracket square is equal to twice E divided by m into V0, and we can have b square d phi by dt is equal to 1 by 2 omega c in bracket b square minus a square here. So finally we can write b square in the bracket 1 by 2 omega c in bracket 1 minus a square divided by b square, the square bracket is squared, is equal to twice E divided by m into V0. So the condition it was to adjust the potential and the magnetic field so that the electron only grazes the anode, not hit it. So from the above equation, the cutoff potential voltage we can write. So it is equal to V0 for cutoff. I mentioned the suffix C here. So this is given by E divided by 8m into B0 square into B square, in the bracket we have 1 minus A square minus B square, the bracket is squared here. Now the condition to have the required thing satisfied here with respect to the cutoff potential, it will be V0 should always be less than V0 suffix C here. So the potential should always be kept less than that of the cutoff potential given by this particular formulation. Now from the equations above, we can also have the cutoff magnetic flux density. So it can be expressed in the form of B0 suffix C. So it will be given by 8 times V0M divided by E. So this is having the square root here divided by B in the bracket 1 minus A square divided by B square here. And with respect to the cutoff magnetic flux density, we have the condition here that the magnetic flux density B0 should always be greater than the cutoff magnetic flux density. So with these equations and the conditions, we are solved with the problem based on to the electron motion in the presence of electromagnetic field. By the next lecture, we shall be covering electric and magnetic microwave equations. So I hope you understand the problem. So it will be a solid base to start with the next chapter here, where we are supposed to learn the principle of operation of microwave tubes based on to the velocity modulation. So for more details, you can subscribe to Ekeeda channel. Thank you.